All right, good morning, guys. Welcome to your first asynchronous lesson of kind of 2023 here. I hope you're enjoying your snow day, and hopefully you can get this done in 30 to 40 minutes here. Today we're going to talk about graphing a sine or a cosine graph. So we're going to take, the unit circle that we learned about last unit with those angles of rotation, and we're going to use that to explore how to graph a sine or cosine function on an XY grid. And then as a little bonus at the end, we're going to bring back transformations, and we're going to start transforming some of these graphs. So as a warm-up, I just wanted to remind you guys, how to graph a transformation of a parent function. Specifically for here, I'm going to graph a quadratic. So if you want to, I would pause the video and then try doing this on your own, and then press play to kind of follow along. The first thing I'm going to do is I'm going to write down a table for my parent function. So my parent function for this one, it's a quadratic, so it's y is equal to x squared, and the table would be -2, 4, -1, 1, 0, 0, 1, 1, 2, 4. The next thing I'm going to do, and I'll switch colors to blue here, is I'm going to label all of my transformations. So you remember HIVO, so I've got two vertical transformations here. I've got a vertical stretch by a factor of 2. I've got a vertical shift down 5. And if you remember from last semester or even higher algebra, we're going to make sure when we apply these to our table that we multiply by 2 before we subtract 5. Order of operations, multiply before you subtract. We do have a horizontal transformation happening too. We have a horizontal shift right 1. So we are going to account for that as well for the x values. So next up, I'm going to apply these transformations to my table. So I'm going to first, like I said, I'm going to multiply all these y coordinates by 2. So I get 8, 2, 0, 2, and 8. Out with the old, in with the new. And then I'm going to subtract 5. So I'm going to, 8 minus 5 is 3, 2 minus 5 is -3, 0 minus 5 is -5, -3, and 3. Out with the old, in with the new. So now that I've done my vertical transformations, my stretching, and my shifting, I'm going to subtract, or I'm going to add 1 to all these x coordinates. I'm going to move all these right 1s. So -1, 0, 1, 2, and 3. Out with the old, in with the new. And then finally, I'm going to graph my new points. So if you want to, sometimes like in class, if you remember, sometimes I would draw circles to represent my parent function. But I would draw them as open circles so as to not confuse with my regular function or the function I'm graphing. So that's my parent function there. I kind of did as a dotted line with open circles. But now I'm going to graph my real function here with these new points. The first one's at -1, 3. Next one's at 0, -3. Next one's at 1, -5, 2, -3, and 3, 3. So you can kind of see the vertical stretch, the vertical shift, and the horizontal shift happening from the parent function, my black function there, to my red function. So this idea, we're going to apply this at the end of class to the sine and the cosine graphs, which we're going to explore today. So sit tight with this concept. So your big learning objectives for today are going to be able to graph a sine or a cosine graph. So we're going to do some exploration there. And then the questions I might ask you in addition to graphing on a test would be find the domain, range, amplitude, and period of a sine or a cosine graph. The way we're going to do that is we're going to transform these graphs, like I said. So today we're just going to vertically and horizontally scale them or stretch or shrink them. So the big idea, while these learning objectives are what you'd be tested on, why is this important? Why is this something I need to know about? Where is a trig or a cosine graph going to help me in the real world? Well, in pre-calculus, we're not going to dive too deep into the why or the what we're going to use these for, other than just rote mathematics. But the big idea really is these graphs we're going to find today, they follow the same type of shape as an oscillation. And an oscillation pops up in the real world a bunch. So if you look at that bottom right picture, it's of a buoy. So if you picture a buoy kind of going up and down, up and down, up and down, if a wave is hitting it, that's kind of like an oscillation, or the same type of shape a sine or a cosine graph has. Same with a heartbeat. A heartbeat the pattern of which is an oscillation. Same with sound waves. So if you're a musician and you want to be a famous guitar player someday, of course you're going to need to know the shape of a sine or a cosine graph before you can become a famous musician. So before we continue, we're going to define two words that I'm going to be saying a ton over the next month or so. So those two definitions are going to be amplitude and period. So an amplitude is the height from the center line to high or low. So like I just talked about, these graphs, they're going to be an oscillation. They're going to go up and down at the same kind of measure. So that distance from the center line of that oscillation to the top or the bottom or the high or the low point is our amplitude. Okay. Now compare that with a period. Now, period is the length the function takes till it repeats. So you can kind of see this oscillation repeating over and over and over again. It can continue going on forever and ever and ever. This repeating, or before it repeats rather, is the period. So just to get ahead of ourselves here, I want to draw special attention to that idea of height and that idea of length. So you can kind of think of length as going from left to right and height going up and down. Or, to connect it to a prior learning, you can think of the amplitude as something to do with maybe like a vertical transformation, and the period having something to do with maybe a horizontal transformation. We'll talk about that more later. So to explore our first graph, which is going to be the sine graph, we're going to bring back in something called the unit circle, which we talked about a ton in the last 2 units. So initially we just learned about evaluating triangles in this top right quadrant in Trig 1, and then we kind of expanded that to all 4 quadrants, and we did, like all students take calculus, we did angles of rotation, we did quadrantals, to really fill in a bunch of angles, specifically special right triangle angles, on this unit circle, based off of that hypotenuse or that radius being 1. So we're going to use that idea really to fill in this table. So we're going to use this unit circle to then fill in the table. So we're going to start here, then we're going to go here, and then we're going to use that table to then finally put our function, our theta comma sine of theta function, on an XY grid. And I do want to emphasize, we're going to kind of take a circle and we're going to put it on an XY grid almost like it's linear, almost like it's, two-dimensional. So it's kind of weird at first, but you'll get used to it. So what I'm going to start with is I'm going to start by evaluating, the nasty word evaluate. I'm going to evaluate theta at each of these points. And you should notice that the angle theta that I'm having you evaluate, it is all quadrantal angles. So just a reminder, the cosine of theta is equal to x. The sine of theta is equal to y, okay? So really what I'm looking for, if I evaluate theta at 0, I'm looking for the y-coordinate. I'm looking for the y-coordinate on my unit circle. So if I graph a terminal side at a 0-degree angle, my y-coordinate is 0. So the first coordinate for the sine of theta is 0, 0. Next up is pi halves. So I'm going to graph a pi halves angle, which would be a quadrantal again. The y-coordinate would be 1. So I'd go from 0, 0 to pi halves, 1. Then I'm going to graph pi. So you'll notice pi goes all the way around to the left half or the negative side of the x-axis. My y-coordinate's 0 again. And then 3 pi halves. I'm going to go all the way around to that negative version of the y-axis. And you'll notice my y-coordinate's -1. And then finally, we're going to go all the way around to 2 pi. And we're back at 0. So we're going to graph this in a sec. But I want you to notice that my graph is just going to continue repeating. So if I keep graphing angles of rotation, if I graph 2.5 pi, if I graph 3 pi, if I graph 3.5 pi, if I graph 4 pi, if I keep going on infinitely, my graph will continue getting as high as 1 and as low as -1, continually crossing over that 0 point, that y-coordinate of 0, which forms what's called an oscillation. So let's go ahead and graph this. So first I'm going to graph the point 0, 0, and then I'm going to label some of these. So I'm going to label this point as pi halves. I'm going to label this point as pi. I'm going to label this point as 3 pi halves, and I'm going to label this point as 2 pi. So I'm really just kind of skipping, I guess, over one notch. And that'll help me. So then I'm also going to graph my y-axis. So I'm going to say that this point up here is 1 and this point here is -1. I don't want it to go any higher than that because my graph isn't getting any bigger than 1 or -1. And then I'm going to graph these points. So 0, 0 is graphed. Pi halves, comma 1 is graphed. Pi comma 0 is now graphed. 3 pi halves, comma -1 is graphed. And then 2 pi comma 0 is graphed. So I've got these 5 points, okay, and I'm going to highlight them for you. These are like kind of our anchor points that help give us our shape of our graph, okay? But then the big question is like, how do I fill in the in-between? So like, does my graph look like this? Does it look like this? Does it look like this? Like, how does it look in between these like anchor points? So I'm going to show you guys how to come up with like, you know, the middle part of these points. But really what I want is for you guys to just be able to graph these anchor points and then generally know the shape in between, just like we do for quadratics and exponentials and all the good stuff. So what I'm going to do is I'm going to pick an angle in between 0 and pi halves. So I'm going to pick theta as pi fourths. I'm going to evaluate theta at pi fourths. Now remember, I'm evaluating this in sine. So I'm evaluating the sine of pi fourths. Okay, so the sine of pi fourths, well, let's go, I guess, over to our unit circle. The sine of pi fourths, let's get some erasing going here, get some clear grid. The sine of pi fourths is going to be like right halfway between, you know, 0 and pi halves. So you can kind of see a triangle forming. So this angle right here is pi fourths. And my sine is my opposite side. So if this is a pi fourths angle, that means this opposite side has to be 1. This adjacent side has to be 1, and this hypotenuse has to be the square root of 2. Okay, so I've got to take my sine of that. So my sine of that is going to be that opposite side, which is 1, over that adjacent, or the hypotenuse, which is the square root of 2. So if I evaluate the sine of pi fourths, I get 1 over the square root of 2, which if you want to rationalize it, you can. Square root of 2 over 2. Okay, but the question is, you know, where does that go on my XY grid? That value of square root 2 over 2, you know, where does it go? Where is it? So I'm going to use a calculator to calculate the square root of 2 over 2. So if you guys want to bring out your calculator and type in square root 2 divided by 2, what you're going to find is that, you know, you get approximately 0.7, right? And this would be a decimal that would like go on, you know, forever. So we're not going to put the exact decimal here, can't, but we're going to round to like 0.7. So this coordinate is at pi fourths, comma 0.7. So if I were to place this on my XY grid, I would place pi fourths here in between 0 and pi halves, and I would place 0.7 like right there, really close to 1. And then if I do the same thing for 3 pi fourths, which I'm not going to for time, but if I evaluate 3.5 fourths, I'd also get square root of 2 over 2. So I'd get a coordinate about right there. So what we find if we graph this is that my grid will kind of almost form almost like a half of a parabola that's upside down. And if I keep going, if I keep evaluating these other points, I'll end up finding that my sine function just repeats values over and over again and kind of oscillates infinitely. Now we only graph until the sine function repeats. So once it gets back to 0, it starts at 0, once it gets back to 0, we stop, we're done. But technically speaking, this thing goes on forever and ever and ever. So that was showing you guys how to take the unit circle, place that unit circle on the table, and then use that table to graph your sine function. We'll do the same for cosine in a second, and I'll be less long-winded. But before we do, I want to talk about these 5 concepts: domain, range, y-intercept, amplitude, and period. So domain and range, we should be able to come up with because we know what those are. Domain is all my x values, so all x's. Range is all y's, okay? And I just said that this graph will keep oscillating between -1 and 1 forever and ever and ever. So that should lead you to believe that the domain is -infinity to +infinity, which means the range, conversely, it doesn't go on forever. It just oscillates between those values of -1 and 1. And make sure you include those values of -1 and 1 because those are a part of my function. Okay, y-intercept, that should be pretty self-explanatory, guys. Y-intercept is just where your graph intersects or crosses the y-axis. In this case, it's at 0, 0. You're just looking for where your x-coordinate's 0. And then we get to those two definitions I kind of started the lesson with, amplitude and period. Remember, amplitude is the value, the number, like the distance from like the middle line, so in this case the x-axis, all the way up to the top or bottom of the graph, the absolute value of that length, or that height rather. So the amplitude for this is going to be 1, so we go from 0 to 1, that's 1. And then the period is the distance over which your graph starts repeating, so like one circular rotation around your circle. So in this case, my graph starts at 0, and then it starts repeating again. It goes back to 0 at 2 pi. So my period is going to be 2 pi. And these are kind of all of the baseline points and ideas and concepts, for this graph of a sine function. So we're going to do the same thing with the cosine graph, and I'm not going to be as long-winded, and I'm going to take some things as assumed for this graph, because I just showed you how to get them on the sine graph, but it is the same thing. I would even challenge you guys, like if we were sitting in the room doing this lesson, I would challenge you guys to try to do this cosine graph on your own, knowing what you just learned about the sine graph, and then checking your work against mine. So if you can't pause the video, try to do it on your own, and then try to come up with the right answer, and then check your work against mine. But this is how we would accomplish the same thing with the cosine graph. So remember, the cosine is the x value. So the first thing is we look at this, unit circle, and then we're going to use that unit circle to fill in, my table, and then we're going to use that table to fill in my graph. Okay, so the cosine of 0, so if my angle is 0, the cosine is going to be the x value at 0, which is 1. So the cosine starts at 0, 1. The next point would be pi halves. So if I evaluate pi halves, the x-coordinate is 0. Then I go to pi, x-coordinate's -1. Then I go to 3 pi halves, so the x-coordinate's back to 0. And then I go to 2 pi, which the x-coordinate's back at 1. So we start at 1, we end at 1. It's kind of the same looking graph, but we're just starting at 0, 1 rather than 0, 0. So I'm going to graph those points. Make sure you graph or label rather your x-axis. I'm going to label those as my quadrantal angles, pi halves, pi, 3 pi halves, and 2 pi. And I'm just going like every other notch, as you can see. You can label them technically however you want, but that's just how I'm going to do it, so that's how I expect you to do it. And then you're going to graph these points. So 0, 1, pi halves, 0, pi, -1, 3 pi halves, 0, and then 2 pi, 1. So you can kind of see that same oscillation between, I'm even going to change my color to show it, same oscillation between, each quadrantal angle and its points. And once again, if you picked a point in between these, so if you picked pi fourths for the cosine, you would find a point right here. So if you evaluate pi fourths, what you'd end up getting is you'd get the square root of 2 over 2, okay? Or approximately 0.7, just like we did in the last, slide. I'm not going to do that for you again, and if you want to bring up your calculator and test it, you can. But ultimately, those points, they form kind of this almost like an upside down parabola that keeps flipping back and forth in between each of these quadrantal angles and the valuations at those quadrantal angles. So the last thing we have to do is we have to define these 5 little terms or find concepts based off of this graph. So my domain is still going to be all real numbers. We just keep going on forever for this. My range is going to still be -1 to 1. My y-intercept, compare this to the sine graph, my y-intercept is going to be 0, 1. My amplitude, the height from the middle line to the top or the bottom, is going to be 1, and my period is going to be 2 pi again. We started at 0, we went to 2 pi before we started repeating my graph, okay? So this is the big idea, these two graphs, the cosine graph and the sine graph. If you know how to graph these, if you know generally how to put these on a graph and tell me these 5 concepts, you're in pretty good shape. Now we're going to bring in the idea of transformations. So to remind you guys, scaling a graph, it really depends vertically or horizontally if the transformations are happening inside of a parentheses or outside of a parentheses. When I say inside of a parentheses, I literally mean next to the angle theta, inside of the parentheses that's containing the input value of your trig function. When I say outside my parentheses, I do mean in front of the trig ratio, so right in front of the sine. Okay, so I could describe this 2 times sine of theta. I could describe that as a vertical stretch by a factor of 2. Okay, so I could describe it like that. I could also say that, hey, this is going to multiply my y coordinates by a factor of 2. Okay, now compare that with the horizontal transformation. Remember, horizontal transformations are always the opposite of what's taking place. That's a multiplication of 2. So we're going to say this is a horizontal shrink by a factor of 1/2. Okay, so you can also consider this, multiply your x coordinates by 1/2. So let's combine these two ideas. Let's take our idea of graphing a sine or cosine function, and then let's apply some of these transformations to them. We're just going to do scaling today. So for this first one, it's asking us to graph sine of 2 pi on the graph given below. So we're going to go through that process. We're first going to graph or use my unit circle to graph the table for the sine graph. So those points are at 0, 0, pi halves, comma 1, pi, comma 0, 3 pi halves, comma -1, and 2 pi, comma 0. Remember, the sine graph starts at 0, ends at 0. Okay, so the next thing we have to do, I'm going to label my transformation, just like we did in the warm-up problem. This is a horizontal shrink by a factor of 1/2, meaning I'm going to multiply these x coordinates by 1/2. Okay, so then I'm going to apply this transformation to my table. So I'm going to apply this. I'm going to multiply all these coordinates by a factor of 1/2. Okay, so I'm going to essentially divide them all by 2. So 0 divided by 1/2 is 0. Pi halves divided by 1/2. Maybe I'll work that out over here. So pi halves times 1/2, excuse me, is going to give me pi times 1, which is pi. 2 times 2 is 4. So pi halves is, we're going to get rid of pi halves, and we're going to bring in pi fourths. Okay, so we're getting rid of 0, we're getting rid of pi halves, bring in our new points of 0 and pi fourths. Then the next thing I'm going to do is I'm going to multiply pi over 1 times 1/2. So this is going to be pi times 1, which is pi, and then 1 times 2, which is 2. So pi is going to turn into pi halves. So out with the old and with the new. And then 3 pi halves times 1/2 is going to be 3 pi over 4, so 3 pi fourths. Okay, and then 2 pi over 1 times 1/2 is going to give me 2 pi over 2, which we could just consider pi, like the 2's divide out. So now I've got all of these old points out of the way. I've got a new set of coordinates there, okay? So what I'm going to do is I'm going to label my graph just like I did in the last problem. I'll even use the same color. I used red before. So I'm going to go every other. So I've got, 0, comma 0. I've got pi halves. I've got pi. I've got 3 pi halves. And then I've got 2 pi. And once again, I'm using like every other to represent these quadrantal angles. And the reason why I'm doing that is because I know that I shrunk my x coordinates by 1/2. So now I'm going to label all of these. I'm going to use like a smaller pencil, but I'm going to label all of these like in between marks as, fourths. So pi halves, pi fourths, 3 pi fourths, pi, and I could keep going. I don't have to though, because if you remember when we evaluated, the biggest point x coordinate we have is pi. Okay, so the last thing we got to do is graph this. So I guess I'll graph this in like green. So I'm going to graph 0, 0. I'm going to graph pi fourths, comma 1. I'm going to graph pi halves, comma 0, 3 pi fourths, comma -1, and then pi, comma 0. And you can see the oscillation forming. You can see like the parabolas that are keep flipping up and down forming, but you can also notice that like my original graph, which I'll do in like blue, I'll do it as a dotted line. My original graph looked something like this. Kind of messed up the 3 pi halves, but my original graph looked like this. So you can kind of see the horizontal shrink by a factor of 1/2. So then the question becomes, how does this impact my domain, range, y-intercept, amplitude, period? Well, domain doesn't get impacted because technically speaking, this graph will keep oscillating forever and ever and ever. It'll keep on going. But my domain doesn't change at all, and neither does my range. My range is going to be from -1 to 1. My y-intercept's still at 0, 0. My amplitude still is 1. We still go from the center line of 0 to the top or the height of 1, but my period changed. My period got shrunk. So if my original period of my original sine function, so my original period is 2 pi, and we shrunk it by multiplying it by 1/2, I've got to calculate that period by multiplying or dividing by 2 my original period to find my new period. So this would be 2 pi, over 2, which is just pi. So my new period will be pi. So that was our introduction to the world of, stretching or shrinking, in this case shrinking a sine or a cosine graph. Let's do one more. So in this next graph, we're going to do a vertical stretch. So still that same process. We're going to graph my parent function, the cosine of theta. So I'm going to graph 0, 1, pi halves, comma 0, pi, comma -1, 3 pi halves, comma 0, and then 2 pi, comma 1. So that's my parent function, cosine of theta. And then I'm going to label my transformation. So my transformation, a vertical stretch by a factor of 2, meaning I'm multiplying all these y coordinates by 2. So this would be 2, 0, -2, 0, 2. So we're lucky when it's vertical. We don't really have a ton of fractions to deal with, which is nice, especially if it's vertical stretch. So then the last thing I got to do is I just got to place these on my grid here. So if my original points, and we kind of have to go off my grid, we're at 0, 1 and -1. So this is 1, this is -1. Now we got to go up to 2 and down to -2, but still should be the same looking graph, just a little vertically stretched. So my first point is going to be at 0, 2. I'll graph that in green. Next point, I got to label my x-axis. Let's do that real quick. So this would be pi halves. This would be pi. This would be 3 pi halves. This would be 2 pi. Once again, I'm going every other. Okay, so then I have 0, 2 already. Next up, I'm going to graph that next point. So I did this one. Next point is going to be pi halves, comma 0. Next point is going to be pi, comma -2. So I got to go all the way down here to -2. Next up, 3 pi halves, comma 0. And then finally, 2 pi, comma 2. So you can kind of see the oscillation forming. It's just like a little stretched out. Like if I were to take the edges of this graph, like almost like the vertices of these parabolas that are flipped, if I were to take those and like stretch them up a little bit by a factor of 2, this is what your graph would look like. So then how does that translate into my domain and range? Well, domain is still all real numbers. We still go forever to the left and forever to the right. The range changed though. My range got stretched, so it's going to be from -2 to 2. My y-intercept changed. Now my y-intercept is at 0, 2. My amplitude changed. My amplitude went from 1. So it was originally 1. Original amplitude was 1. But if I multiplied it by 2, my new amplitude is going to be 2. I got to multiply that 1 by 2, and I end up getting 2. But my period didn't change. My period still goes from 0, to 2 pi. So my period changed. So hopefully we see the connection. A vertical stretch is going to impact my amplitude, or horizontal stretch will impact my period. So to recap, I was hoping today that you were able to graph a sine and a cosine graph, be able to state the domain, range, amplitude, and period of a sine or cosine graph and the y-intercept, and then also vertically or horizontally stretch or shrink or scale a sine or a cosine function by a given factor. If you can do those 3 things, you'll be in good shape when we return from all this snowiness. So the last thing you have to do, you got a little tiny quiz to take. I think it's 4 questions. I think some of them are even multiple choice. Just make sure to complete that quiz. There is an attendance component with that quiz, so if I don't see you did it, or even attempt it, we'll have to mark you absent per Mr. Erickson's rules. So just make sure to get that done, and then I will see you guys on hopefully Friday. We'll see if I can shovel my way out of my house here with all this snow. Hope you guys enjoy the rest of your snow day. Hopefully it just didn't take up too much of your enjoyment there, but we will see you when you get back.